So in previous talks, I've talked about modeling the deterioration behavior of structural elements based on visual inspection data. In this talk, we're going to see how we can extend this application to go beyond structural elements, such as we can get the deterioration estimate for an entire bridge, so the overall deterioration state, and also the overall deterioration state for an entire network of bridges. So my name is Zachary, and this research project has been published recently under the same title of this presentation. So the breakdown for this presentation is going to be as follows. First, we're going to have a look at the context and objectives. And by context, we mean some of the characteristics of visual inspections and our objective in working with visual inspection data. After that, we're going to have a quick recap for the element level deterioration analysis. So what are the bases of the method and how it's done? And then in the following section, we're going to have a look at the network scale analysis. So how we can extend the analysis from an element level toward like bridge level or even a network level, which we're going to see in details. And finally, we're going to see a demonstration which is done on a real database from the network bridges in the province of Quebec. So visual inspections is a monitoring technique that's utilized on a large scale to monitor the deterioration state or the health state of infrastructures over time. And when we are saying a network, we mean a number of bridges. So in our case, we have around 10,000 bridges located in the province of Quebec. Some of these bridges are similar to each other in terms of material or traffic load, while others are completely different. Now, in order to have some intuition about like how visual inspections are performed, we need to know like what's within each bridge. So for each bridge, we have the two main groups of elements. So we have elements that are directly associated with the structural safety of the bridge, such as the beams and like the slabs. And we also we have elements that are associated directly with the serviceability of the bridge, such as the safety barriers or the pavements element. So each one of these category of structural elements is composed of a number of elements. So we have we could have 2 slabs in a bridge, or and so on, or 20 beams and so on for each one of these categories. Now the inspections are performed at the element level. So an inspector would go and visit a bridge at a given year. So for this example, we have a year 2008. An inspector would go and perform a visual inspection on the element, in general, it goes for all the elements. And these inspections are reported for each year. So the inspections could happen every 2 years or every 3 years, depending on the frequency or the importance of the bridge. So in this case, we have every 3 years, and it carries on. Now, for some structural elements, we have also the an intervention would happen. So we have this information. We know what kind of intervention that took place, and we know when it took place. So we have these, and things carry on. So in previous presentations, we've talked about all these details, how we can model the effect of interventions, and how we also can model the deterioration behavior. So we have an estimate for the deterioration states at the element level. Now, our objective in this study is really simple. We want to extend these deterioration state estimates beyond structural elements to get the deterioration states for the structural category, as we saw earlier, for example, for the beams or the slabs, and so on. And we also even want to extend it further to get the overall deterioration state for a bridge, and even for a network of bridges. So this is the main objective of this research work. Now, in order to tackle this objective, we have to take a step back and have a look at how we are doing the deterioration analysis at the element level. So what we've done in the previous research work that has been already published is that we've described the deterioration behavior using a kinematic model. This kinematic model is described by the kinematic equations for the condition, the speed, and the acceleration. Now, if we want to write down these equations in a different way, in matrix form, makes it easier to look at, we see xt, which is the deterioration state at time t, a is the transition matrix, and xt minus 1, which is the deterioration state at the previous time step, plus wt, which is the process error. Now, in order to be able to describe or use this kinematic model, we relied on the state space models. Now, state space models, it's composed of two models. The first model is the transition model, which is described in similar equation as we see above, or the same equation, which is the kinematic model equation, as we see here. And the process error in this case is described by a zero mean and covariance matrix Qt. Now, the way this goes is that we have a prior estimate for the condition at time t0, and we are using this transition model to get the estimate at time t1. Now, so far, we haven't used the observation. So if we have an observation at time t1, we use the observation model, which is described by yt equals to c, the observation matrix, multiplied by xt, the deterioration state at time t, plus vt, which is the observation error. And in this work, we describe the observation error by a zero mean and a variance associated with each individual inspector. So the observation is dependent on the inspector that performed the inspection. So using this observation model, we can update our estimate for the condition, and we can get the posterior for the estimate for the condition of the structural element. And we carry on the same way. So we use the transition model to get the next estimate. And then if there's an observation, we use the observation model to update the model estimate with this observation. And this is done mainly through the Kalman filtering approach. However, there are other characteristics, other modifications that relate to this. So in order to have an overview of these modifications, again, we have the inspection data. For an element E, we have the inspection data represented by y tilde, and y tilde here represent the bounded conditions. So like in general, visual inspections are evaluate the structural element given like certain bounds. So it says that 25 is a poor condition and 100 is a perfect condition. So these are what we call bounded visual inspections. Now, in order to apply our framework, what we've done is that we've used a transformation function, call it a transformation function O, which is like kind of a step function that would allow us to transform our bounded observations into an unbounded space. So we get like the observations y, or the inspections y. And after that, we will be able to pass our observations into the deterioration model, which is like, we call it SSM, or even like SSMKR. These studies have been, again, already published. And the SSMKR refers to using kernel regression alongside the SSM model that I've described earlier. So using this deterioration model, we get the deterioration state estimate at time t for that particular structural element. And then what we do is that in order to be able to interpret the results, we back transform this deterioration state estimate into the bounded space. So we back transform it using the same step function into the bounded space. We have our deterioration estimate between the bounds that are well known for the inspectors. So as I mentioned earlier, that the inspections in reality are bounded to refer to what is a poor condition and what is a perfect condition. So these are, in general, these are things that have been described in details in previous work. Now, to look at an examples for element level analysis, let's see the inspection data here. So on the x-axis, we have the timeline on a yearly scale. On the y-axis, we have the condition. The condition starts from 25 for poor condition up to 100 for perfect condition. However, here for visual purposes, the axis started at 40. The inspection data are reported by the blue points, as we see here, and each point is associated with an inspector. So the inspector, each inspector have a unique ID in this case. So the uncertainty associated with each inspector has been estimated using the framework I've described earlier, using a procedure within that framework. So these are the estimates that are obtained for the uncertainty of each inspector, and the deterioration condition estimate for this structural element is represented by the red dashed line, and the confidence interval around it described by the red area for 1 standard deviation and 2 standard deviation. So this is like in general how things look like at structural element level. Now again, as we mentioned, that we also have on the structural element level, some of the elements have underwent an interventions. So if we look at this case, so this is for a case for a beam that underwent reparation, and this is again from a real case. So we know that the intervention took place at the year 2011. And we have, again, the inspection data reported by the blue point. This is for the condition, and the x-axis is the timeline on a yearly scale, and the y-axis is the condition. And we also, as we described earlier, that we are using a kinematic model, so we actually also characterize the deterioration speed. So the figure on the right represents the deterioration speed, which we have, again, on the x-axis, the timeline, and the y-axis is the deterioration speed. And again, the intervention is at year 2011. And in this example, I'm going to show that we are actually able to quantify and model the effect of intervention on structural element level, as we see for the red dashed line for the condition estimate for the this structural element, and even for the effect on the deterioration speed as we see it on this slide. So again, all of this have been done earlier, but again, the application was limited to an element level application. So here right now, what we're going to see is that how we can take this to a network scale application or network scale analysis. In order to do so, what we need to do is, first, when we are talking about a network scale, we are dealing with a large amount of data, so millions or like hundreds of thousands of structural elements and millions of inspections. So some of these inspections might be missing, some we might have some inspections that are erratic, and even we might have some missing interventions report. So like we have interventions that are unreported. So how we need an approach to deal with that. And the other thing, we need an approach or an aggregation method that would allow us to aggregate the deterioration states estimates at the element level, to take it to a category level, and then like even to take it to a bridge level, and even finally to a network level. So these are the two prerequisites. So first, we're going to look at how we can handle missing data. And the most important part in here, so again, missing data, the most important part is the missing interventions. So we're going to talk about that. So missing interventions could be the prior knowledge about the effect of an intervention is not available. So as we saw the jump in the condition, we have created a model that was able to estimate the jump associated with each type of intervention. So we can quantify what's this jump that we can. But however, in some cases, we might not have enough data to quantify this prior knowledge. So this prior knowledge could be missing. So we need to kind of handle this. And the way we handle it is that we say for a given type of intervention on a given category of structural elements, if we don't have the effect of this type of intervention on that structural category, we look to the closest thing. And the closest thing is the expectations, could be the expectations of the effect of interventions of that type of intervention on a similar on other categories that belong to the same group of category of structural elements. So further explanation can be done, but the point here is that dealing with this issue is not that complicated. We can replace the unknown prior knowledge with the expectation of other of the same type of interventions on other structural elements. So that's possible. The other point is that, or the other missing intervention information could be, is the type of intervention is not reported. So this, we can deal with it with the log likelihood. Now, I'm gonna explain about this later on. But getting to the third point about missing interventions, the intervention date and the type are not reported. So here we have inspection data. The inspection data shows a jump, but there's no mention of any intervention. So we don't know, we know when the jump happened, but we don't know when the intervention actually happened. And we don't know what kind of intervention that happened. So in order to talk about, so we're gonna explore this third point under the unreported interventions. So this is an example for data, visual inspection data, that has, again, the x-axis is the timeline, and the y-axis is the condition. And we have the inspections reported by the blue points. And for this case, we have no mention of an intervention in the interventions database. So there is no information at all about the interventions. However, from visually, we can see that an intervention could have happened at 2012, 2013, or even 2014. But we don't know when it actually happened. So one way to handle this is just run the model and perform the prediction as is. But the issue is that we get a kind of a biased estimate for the condition, because the condition would try to kind of fit the data based on the uncertainty and so on. So it would try to pass in between the inspections. But again, and even if we look at this case, the inspector at 2011 is the same inspector at 2017. So the potential that an intervention happened is really high. So how we handle this? The way to handle this first is to determine that there is a trend, an upward trend. So again, like visually, we can see that the element was at a certain condition, and then the condition has improved and continue in the same improvement way. So this is not, the potential of this jump being noise is really low. But we need to kind of have a criteria to tell us that, yes, there is an upward trend based on the inspection data that we see here. So this criteria is defined in these equations. So the criteria basically is delta, and delta represents basically the ratio between the sum of the positive improvements over the sum of all changes. So the sum of positive changes, again, over the sum of all changes in the absolute value. So the sum, so the changes are described as the difference between two consecutive observations, and delta t here represents because observations not necessarily happen every year, they could happen every 2 years, so that's why delta t is here. So we look at the changes between two consecutive observations, And in the case for the positive changes, we consider any change that is positive, we report it. Otherwise, it's 0. So this is basically the criteria that would tell us that, yes, there is a positive trend in the inspection data. And so we've determined that there is an actual positive trend. So now, and we determine that there is an intervention at a given year. How do we determine the type of intervention? We determine it using the log likelihood estimate. So because we have a limited number of interventions that could take place on a given structural category of elements, we can try to plug in the effect of each type of intervention and estimate the log likelihood. This is, there are further details and further characteristics that are detailed in the paper, but however, this is the main intuition, is that we plug in the effect and we estimate the log likelihood. And at the end, we chose the intervention that has the effect that maximizes the log likelihood on one structural element. So based on these criteria, what we get for, again, the same inspection or the same case, what we get is that there is an intervention in 2012, and that the effective intervention is modeled as follows. So this is for the missing interventions, unreported at all. There are further details that characterize like how we deal with other issues, but like these are the kind of highlight of that part. Now, we talked about missing data. Now we want to talk about handling outliers, because again, we have a very large data set, and a lot of data could be, some of the data could be erratic information, or could be like human error. So whenever we see an outlier, and just to reiterate, so for an outlier to be classified as an outlier is that whenever the model, there's a numerical instability in the model. So it like basically the model can't perform the prediction because of the presence of such an observation. So that's why we've defined, and that could happen whenever we have a large jump in the observations. So this large jump could be due to possibilities. One of these possibilities is that this large jump is a missing intervention. So we need to do the processes associated with missing intervention. But however, if we couldn't find any clue that this outlier is actually a missing intervention, then we need to remove the outlier data so that we can actually perform the prediction and the forecast in the framework. So, and the removal of the outlier is basically based on a weighted average. So the equation or the criterion that we've defined is that to identify at which time the outlier happened is the argmax over t, and t again is the x-axis, and it's the difference between each of the observations minus the weighted average, y hat. And this weighted average is weighted based on the uncertainty of each inspection. So basically, for an observation to be an outlier, it has to be really far away from all other observations, and the inspector that performed it has to have a large uncertainty. So this is the main criteria, or the best criteria that we can derive based on the available data in a given element. So that's for handling outliers and handling missing data. Now, again, there are further details and further conditions about like what determines an outlier, what determines the missing intervention, and how we handle both. Each described in further details in the paper. Now in the following subsection, we're going to talk about how we can aggregate the deterioration state estimates. So as I've showed earlier, for each element, I have my bounded inspections defined by y tilde. So in this example, I'm going to see I'm going to process 3 elements at the same time. These 3 elements belong to the same category. So for example, this could be the category of slabs. So I have three slab elements. Each of them has their own inspections over time, bounded inspections, and they are all within the same bridge. So I do the same steps. I pass each one of them into the transformation function, the step function I've talked about, and that would give me the unbounded observations for each one of these elements. And then I plug these observations into my deterioration model, and I get the deterioration state estimate for each one of these elements. Again, nothing so far is different. Now, the part that we can aggregate these estimates is about to start. So here we have, so these estimates for each one of these elements, we can aggregate them based on a weighted sum of the Gaussian densities. So these, each one of these deterioration estimates is Gaussian. So we can have a weighted sum of these Gaussian densities based on weights lambdas, as we see here. We can have a weighted sum that would define the, and the lambdas would define the contribution of each of these deterioration state estimates to the overall deterioration state estimate. So we obtain the merge for all the deterioration state estimates. And this is again a Gaussian. And what we do finally is that we pass this into, we back transform it using the step function into the original space, or the space where, again, the inspectors know how to interpret. So that's from 25 to 100 in this example. So that's how we merge we merge 3 elements, and it could be extended to an n element. But this just an example for demonstration purposes. Now, the Gaussian mixture reduction approach that's utilized, the equations for this approach are described in the paper, but the concept is really a weighted sum of Gaussian densities to obtain a single Gaussian density, and then we back transform to the original space, and we get the data. So this is really the principle of the method. Now, if we go and see a real case study, again, we've talked about the breakdown for like what's within a bridge, and the elements and the visual inspections, and we've talked about that we use these visual inspections to get the deterioration estimate for each element. Now, what we want to do is to extend this deterioration state estimate to get the deterioration state estimate for each category, so for the beams and so on. And even further for the group of categories, such as the group of elements that are responsible for the structural safety of the bridge or serviceability of the bridge. So let's look at an example for each. We have the first example, the concrete slab category in this particular bridge. So on the left graph is the condition, on the right the speed. On both graphs we have the timeline is on the x-axis on the yearly scale, and the y-axis on the graph on the left represent the condition, on the right represent the speed. The inspection data here are reported by the blue triangle with the uncertainty. So this is really an aggregation for all the observations performed on the elements within this category. So that's why it's represented by a triangle measure. And as we see for this category example, we have actually an intervention. So that intervention took place in 2015. And if you want to see the deterioration model estimate, it's represented by the red dashed line, and the confidence interval, as we see here, for both the condition and the speed. So that's for one category. If we want to go further and go for all the primary elements, or all the elements that are responsible for the safety of the bridge, We have the observations represented by the blue diamonds, as we see here, and the uncertainty. So these are the aggregated observations for all the elements within the bridge. And these elements are, again, responsible for the structural safety, such as like an aggregation of all the beams and slabs and so on. So these are all the observations. The intervention have happened in year 2015. And again, the deterioration model estimate is represented by the red dashed line and the confidence interval for each the condition and the speed in this case. Now, if we want to extend this even further, we can actually estimate the deterioration state for a network of bridges. And this case study we've done for 7,000 bridges. So again, the way to look at it is that each bridge has elements that are responsible for structural safety and has elements that are responsible for the serviceability. So the way we looked at it is that even for a network, we're going to do it the same way. So we're going to aggregate the deterioration state estimates for all the bridges and within the same kind of type of elements. So all the structural safety for all the bridges and all the serviceabilities of elements for all the bridges. So to see an example how it looks like, so here we have a graph, again, a figure with the left figure as the condition, the right figure is the speed, and the timeline is on a yearly scale on the x-axis, and the condition on the y-axis from 25 to 100. And here we represented the observations by a magenta diamond, and this, like, again, to represent the aggregation of all the elements within the primary elements for all the bridges are at this kind of condition. So as we see here, this is like the overall for the network. Now, if we want to see the deterioration condition estimate, we see it in the red dashed line, and the confidence interval around this estimate, each for the condition and the speed as well. Now, further interpretation of these results and further analysis can be shown in the paper, but for this is like really to highlight one type of possible analysis that we can do. Now, finally, in conclusion, the key contributions of this work is that we've designed a network scale deterioration model that would allow us to estimate the overall deterioration condition and speed at a bridge level or even at a network scale. And we've also designed a model or a method or an approach to handle the missing data and outliers. So all of this would enable the potential for performing network scale planning based on visual inspections.